Hey guys, welcome back to my channel. How's it going? In our last video, we explored the fundamental principle of counting and tree diagrams. Today, we're gonna put this knowledge to work by solving two interesting problems that demonstrate how powerful this principle can be in real-world situations. So the problem number one is the library example. Let's imagine a library that needs to create a unique identification codes for its books. Each code must start with 2 letters. So the first requirement that each book starts with 2 letters, from A until the Z. The second requirement is that it followed by 3 possible digits. 3 digits from 0 until the 9. And then it should be ended with 1 possible letter from A until the Z. So it starts with 2 letters, contains 3 digits in a row, and then ends with 1 letter. How many different codes can they create? Let's solve this step by step. First position has 26 possible characters. The second position has also 26 possible choices. The first one has 26 possible, the second one has 26 possible, the third one has only 10 possible choices because that's about choosing the digit. So the third one is 10 possible choices, the digits from 0 until the 9. The fourth one, also 10 digits, the same goes for the fifth one, is 10 possible digits. And the last position is 26 choices, since we're considering the character. The sixth choice is 26 possible, from A until the Z. Now we just need to calculate the total combinations, that is essentially the multiplication of all possible choices. N1, N2, and this way until the N6, which equals to 10 cube times 26 cube, which equals 26 cube times 1000. And here you are free to use a calculator, and calculating this, it will be 17,576,000 total number of combinations possible. So let's visualize this with a tree diagram. I'm just joking. You can do it because it will be enormous, but it's still helpful here because you're essentially using the tree diagram thinking. You're using the same approach as we did before without explicit visualizing of our combinations, but the approach still remains the same. Now let's take a look at the second example. A password system which requires users to create passwords. That first off must be exactly 4 characters long, so the length of our password should be 4 characters. The second requirement is that it can use lowercase letters from A until the Z or digits from 0 until the 9. It's A until the Z or the digits from 0 until the 9. And it must contain at least 1 number. Must contain at least 1 number. This is trickier because of at least 1 number requirement. Let's solve it by using complementary counting. First, we need to find the total possible passwords without any restrictions, as we did before in our last exercise. For this, we just need to find how many characters each position can take. Each possible position can take 10 plus 26 choices, which equals 36 outcomes, because we have 10 possible digits and 26 possible letters, 36 possible outcomes in total. So we need to calculate 4 such positions. It will be 36 to the power of 4, which equals 1,679,616 possible combinations. Now we just need to subtract the number of passwords with no numbers. And if we don't have any numbers, each position is essentially 1 letter. So in case if we don't have any numbers, each position will be only 26 possible letters. If we need to find the total number of ways in which we can make up the passwords without any numbers, it will be 26 to the power of 4, which equals 456,976 possible combinations. And therefore, in order to find the valid passwords numbers, we just need to subtract the all possible numbers, which is n minus n bar, which equals to the amount of passwords without any numbers. It will be 1,222,640 possible ways. And why these examples really matter? These problems demonstrate key principles. First off, breaking down complex problems into simple choices. Second off, using complementary counting when direct counting is difficult. Third, recognizing when order really matters. And the last one, applying the tree diagram even when drawing the full diagram is not practical. The applications of these problems appear in cryptography and security systems, database design, inventory management, scientific research, and even in the software testing. But please watch out for overcounting by missing restrictions, undercounting by forgetting possibilities, missing the least or the exactly distinction, and forgetting to consider order when it really matters. The fundamental principle of counting becomes even more powerful when combined with other techniques like complementary counting. And in our next video, we're going to explore permutations and how they relate to these concepts. Thank you for watching this video. I hope you found this video helpful. If you have any questions, please leave them in the comment section below. For more technical discussions, please join our Discord community, and you can also connect with me on LinkedIn for updates on future content or any other discussions. See you in the next episode. Please take care. Bye.